Okay, hello everyone. Welcome to lecture 2. There's a few things I want to cover this lecture. Kind of mushed in together, kind of reflects what how the notes you'll find on the drive are structured. So we're moving away. That partial fraction stuff we did last time is pretty much the only non-calculus stuff we're going to do here. Everything else from here on in is going to be all differentiation, integration, or a combination of the two. So let's get started and have a look at what we're going to have a look at. So the first thing we're going to look at here is the derivative derivatives of e to the power x and ln x. So these are just two extra derivatives that we're going to add to our table of standard derivatives. I'm going to expand a wee bit beyond this guy and this guy to add sort of other stuff that goes on inside here. So the cool thing about the exponential function e to the x is that if we differentiate it, we get the same thing. So that is to say that for the graph of e to the power x, let's see how well I do here. If we draw a quick graph, then the y value of this point that I've picked for x is going to be e to the x, but also the gradient coming through this point is going to be equal to e to the x as well. So it's quite a cool function in that it only has one piece of information really per point, one number per point to remember. We'll also find the implication here is that if when we differentiate f of x and we get if we differentiate e to the x to get e to the x, then if we integrate e to the x, we should get e to the x as well. And if you remember, we spoke before about how the integral of a function is equal to the area underneath that graph. Well, that means that at this point, from 0 to this point, the area underneath it is equal to e to the x, and the gradient is equal to e to the x, and the height is equal to e to the x. So it's a kind of compounded function where everything we need to know is kind of given to us straight away. So this is all well and good, but what we might want to do is say, well, what happens if it's slightly more complicated than this? So I kind of state it in the notes, I state it kind of more mathematically sound than this, in that I say that if f of x is equal to e to the g of x, say, then using chain rule, f dashed x is going to be equal to let's roll back a wee bit there. Let's say if f of x is equal to e to the u, then f dashed x should be equal to d f of x by du times du by dx by the chain rule. In other words, we're going to differentiate this with respect to u, which remember we said that if we differentiate with respect to x we get the same thing, and we're going to differentiate the thing inside the exponent with respect to x, so that's going to be equal to e to the u du by dx, or to translate it to this language, f dashed x is equal to, if f of x is equal to e to the g of x, so e to the power of some function of x, whatever's going on up here, then f dashed x is equal to e to the g of x, so this thing stays exactly the same, times g dashed x. So in other words, we just differentiate whatever's in the exponent and multiply it out the front. So that's a general rule. We could write that slightly differently, could we? Yeah, no, this will be fine. This is a general rule for taking exponent of any function, but we're going to want to settle this down a little bit. We're going to talk about applying the chain rule a little bit later on in this lecture, but for now, let's calm it right down. And instead, let's say that we just augment f of x to go from e to the x to e to the ax plus b. So some linear function, something that's been turned into a straight line equation. Multiply it by something, add a constant to it, and then what do we get? So f dashed x then, if we follow this rule here, is going to be e to the x plus b times, and then this says we're going to, whatever's up here, we're going to differentiate. So differentiating a to the x plus b, well the b is going to disappear because there's no powers of x attached to it, and the x is going to disappear to leave the a that's attached to it, so it's times a. So that's a e to the ax plus b. So it's quite similar to the trig stuff that we did. In that, sorry, that's my dog reacting to someone opening a door about 4 blocks away. So it's quite similar to the trig stuff in that if there was something multiplying the x within the bracket, the thing just came out and multiplied the function out in front. Simple as that. So a quick example, because I don't think it takes much talking about. Let's do f of x is equal to e to the ax minus plus 3. That implies applying a rule that f dashed x, we're just going to multiply this function by whatever's here, because when we differentiate this thing, everything disappears but the a. So it becomes a e to the ax plus 3. So we're going to see that e to the x is quite a, because all this stuff is quite a special function, we quite like it. It pops up a lot in a lot of physics and maths and engineering and stuff, because when you differentiate it, all you do is you increase its size if you like. It'll have the same shape. So if I were to do, let's do a wee graph. So if this was e to the ax plus 3 is equal to f of x. I might run out of room here, so bear with me. Oops. And that would be a e to the ax plus 3 equals f dashed x. So all it does is change its shape. So that's not, because it's an exponential graph, that's not so remarkable, doesn't look that dramatic, but we're going to, well, are we going to see? We may see that there are some cases where this is really very important, where there's stuff we can put in that exponent that gives it a non-strictly increasing shape, and therefore makes it very interesting that all we do is stretch this thing out by whatever number was in front of the x. So let's have a talk about ln x. If f of x is equal to ln x. So I should say that there are definitely proofs for all this stuff, but they're quite lengthy and a wee bit kind of tricksy, so I'm going to leave them for now. Just take me at my word that these are the true derivatives of what we should get here. So the derivative of ln x is equal to, quite nicely, just 1 over x. Now we're going to see in a little bit, this is one of these times where, although differentiation is usually our first port of call, that actually integration might have been a better place to start with, because we're going to see that this actually fills in a gap in our knowledge, and that previously if we tried to integrate 1 over x, well 1 over x is x to the minus 1. To integrate we add 1 to the power and divide by the new power, so we would get minus 1 plus 1 is 0, so it would be x to 0 over 0, which is impossible, we can't do. But this fills in a little gap in our knowledge. This tells us that oh, it's actually a different rule for x to the minus 1, which is 1 over x. It becomes ln x when we integrate it, or the other way around. When we differentiate ln x, we get 1 over x. Similarly, if we do f of x is equal to ln of g of x, so just some other function going on there, so it could be ax plus b again, which we're going to concentrate on, but it could also be sin x or e to the x or something like that. Then f dashed x is going to be, well, from the chain rule we're going to differentiate the outer function with respect to g of x, so it's going to be 1 over g of x, so ln x becomes 1 over x, so ln g of x becomes 1 over g of x times g dashed x. So that's equal to g dashed x over g of x. So that's quite interesting because it gets rid of all the logarithm stuff. It becomes just the derivative of the function on the inside over the original function on the inside. And you don't have to worry about any of this stuff. Okay, so let's look at our more relevant one. Let's do f of x is equal to ln ax plus b. Well, f dashed x then is going to be, so ln x becomes 1 over x, so ln ax plus b becomes 1 over ax plus b, and then times that by g dashed x, so that's going to be b disappears, x disappears, leaves the a, so that tidies up to a over ax plus b. Now this is interesting, something to watch out for actually, is that in the case where b equals 0, well let's have a look at it. F of x is equal to I think let's just do the full thing. ln ax plus b, f dashed x is equal to a over ax plus b. Set b is equal to 0 implies that f dashed x is equal to a over x, which is 1 over x. Which is another one of these kind of mind-blowing things about with logarithms that doesn't make any intuitive sense. So this is essentially saying that the gradient of ln x, the gradient of, so any case where b is equal to 0 means it would just be ln a of x, ax, sorry. So this means that the gradient of ln x and the gradient of ln 2x and the gradient of ln 10x and the gradients of ln a million x are all the same for the same value of x, which seems a bit counterintuitive, but it kind of makes sense So I'll do it last wee bit. F of x is equal to ln ax implies that f dashed x is equal to a over ax, because b is 0, which is 1 over x. Well, if we remember from laws of logarithms, ln a plus ln ax is actually equal to ln a plus ln x. So then we've split this into a part which has no gradient. A is a constant, so ln a is a constant as well. So a part that has a gradient and a part that actually changes. So this is implying that whatever a is, there's only one part that changes, and therefore only one part that actually gives it a gradient. So this ln a is just a flat line that the logarithm starts on. Can I fit in a wee graph here? Maybe. I'll do it up here. No one. I'll try and do it quick here. So if this is the graph of ln x, then this is the graph of ln ax. And all that's happened is this thing has been shoved up by a value of ln a. You just add that on, that's all. So let's do a couple of little examples. Got my pen mixed up. So let's do a couple of examples. Let's try and let's do y is equal to e to the 5x plus 3 minus ln 6x minus 2. Something like that. Okay, so dy by dx then is going to be equal to, so this number comes out the front, 5e to the 5x plus 3, so that's the derivative of this term. The derivative of this term is going to be minus 6 over 6x minus 2. So that number comes out. So whenever these things are linear terms, whether it's for trig, whether it's for logarithms, and whether it's for exponentials, you end up just taking this number out and putting it in front and then multiplying that by whatever the derivative of the rest of it would be. Do a couple of weird ones. Y is going to be equal to ln x squared plus 5x plus 6. Okay, so we could think about this as a chain rule thing, but let's see if we can be slightly clever than that to avoid doing that. Let's factorise what's on the inside. I like to factorise, so that's going to be x plus 3 and x plus 2. And then using the laws of logarithms, so we can split that up into two logs. So ln x plus 3 plus ln x plus 2. And then we can differentiate that quite easily. So, whoops, dy by dx is going to be equal to, so the number in front of the x here is 1, so it's going to be 1 over x plus 3 plus, and again, 1 over x plus 2. And that'll be you. And then let's do one of the more complicated things. Let's do ln cos x plus e to the 4x equals f of x, let's say. So f dashed x is going to be, we'll remember earlier on we said that it's going to be equal to f dashed x over f of x, or rather, sorry, the derivative of this thing divided by this thing. So the derivative of this thing is going to be minus sin x plus 4e to the 4x divided by cos x plus e to the 4x. So you can flick back, rewind this a little bit and have a look at that. Or, let's just show you this thing here. I said that when we differentiate ln of some function g of x, it's equal to this function differentiated divided by the function again, and that's what we've done here. This function differentiated is minus sin x plus 4e to the 4x divided by the whole function, cos x plus 4e to the 4x. And these things can get more weird and wonderful than that. I'll let you guys take a look at the questions and the notes and have a practice at a few of those. For now though, I'm going to move on. Oops. So the chain rule. The chain rule we can extend a little bit further. We've spoke about the chain rule before, but we can push past what we've done before and add extra layers to what we've got. So let's say, let's do a simple chain rule. Simple chain rule. Example. So f of x is equal to e to the cos x. So this is actually like and not like what we've done before, in that I've introduced the exponential function here, but that should be easy enough to handle. So we're going to call that e to the u, and call that y as well. We do dy by du is equal to, well, y in terms of u is e to the u, it's going to be e to the u, and du by dx, well, u is equal to this cos x thing up top, is going to be minus sin x. So dy by dx, if we want to differentiate y with respect to this variable x, we get that by taking dy by du and multiplying by du by dx. In other words, how fast does the function change with respect to u times how fast does function u change with respect to x. Kind of makes a wee bit of sense that would be the case. You're changing one of the substituted variables, you're seeing how fast that changes, and you're saying, well, actually further to that, the other thing's changing as well, so the speeds mount up. So that's going to be equal to dy by du was e to the u, and du by dx was minus sin x. So that's going to be minus sin x e to the u, and then we want this in terms of x only, so that's going to be minus sin x e to cos x. And there we have it. So that's a simple chain rule example. What we want to look at are more complex cases. So I'm going to do a more complex chain rule example. And all I mean by a more complex chain rule example is that there are extra layers that we have to think about. So let's do y is equal to, let's start with sine squared x plus 2. And let's do that cubed. And I'm going to call that u cubed. So we're calling that u cubed because already I don't like that list going on, but if it was simply u cubed, that's something I know from the power rule in my calculus how to differentiate. So then we say that, well, u is equal to all this stuff in here, sine squared x plus 2, but I don't like that either. I'm going to call that v squared plus 2. Then finally I'm going to say that v is equal to sine x. So I've had to do extra layers because upon taking the substitution of u out in the first line, I've not made it something I can differentiate straight away. I don't have that off the cuff to go. So I do another substitution to make it even simpler. So it takes this trigonometric thing, takes this horrible trigonometric thing first of all, makes it a polynomial, takes this horrible trigonometric thing, makes it a polynomial, and then we're left with a trigonometric thing at the end, sorry, but a really simple one. So we're going to say that dy by dx, just like the chain rule, is going to be dy by du. So multiplying it by differentiating by the first layer, the first substitution, but then multiplying that by the second substitution. So by du by dv, and then by dv by dx. So we've just got an extra layer. And the idea is that these ones should always cancel. Du in the bottom, du in the top, dv in the bottom, dv in the top. They cancel. You're left with dy by dx. So dy by du is equal to 3u squared, which I might just put that stuff back in. So it's going to be 3, and u was sine squared x plus 2. That's good. Du by dv, so that's going to be differentiating with this with respect to v is going to be just 2v, and then again put the x stuff back in, so that's 2 sine x, and then dv by dx. Well, v is just sine x, so make that cos x. So then dy by dx, following this instruction here, is just these three things multiplied by each other. So I'm going to do it in kind of reverse order. So it's going to be cos x times 2 sine x, oops, times 3 sine squared x plus 2 squared. And then neaten that up a little bit. So it's going to be 2 times 3 is 6 sine x cos x sine squared x plus 2 squared. So that is the answer to differentiating this thing. But the key thing to note is that this is correct. It is not pretty. 6 sine x cos x squared x plus 2 squared. Not a handsome thing at all by any means, but it is correct. It's the right answer. There are perhaps things we could do to make this a bit nicer. Sorry. 2 sine x cos x is sine 2x, so we could make that 3 sine 2x this thing, but that's maybe an argument worth having, whether that's actually nicer or are you just making things different for the sake of making things different. Okay, I'll maybe do another example. Let's do, I'll do a strange one. I'll do strange notation. So R is equal to cos squared of e to the t squared. Find dr by dt. Oh, I think I've maybe made this a 4-level one. So we're actually only going to be asked to do 3-level chain rules. In theory, chain rules can be of any length. I'm just going to pile on with this and see where it goes. You'll see it's actually the same kind of process. It's just extra steps, that's all. Not new steps, just a requirement of more. So the simplest thing we can do here is say that R is equal to u squared, where u is equal to cos e to the t squared. So that's what that means. So then I'm going to say u is equal to cos of v, where v is e to the t squared. I'm going to say that v is e to the w, where w is t squared. And then that'll be us. We don't have to go any further because I can differentiate that fully. There's no reason to do a chain rule step on that step, so I can just charge ahead and differentiate it. Okay, so I need to do that, but that, d that by d that, d that by d that, d that by d that, and then d that by dt. So dr by dt, just to keep myself right, is going to be dr by du times du by dv times dv by dw times dw by dt. I hesitated there because I forgot that we're actually going for t and thought, oh, we've got 3 here. Have I got not enough? I forgot we're going all the way to t, not all the way to w. So dr by du is going to be equal to 2u. So differentiating this with respect to u is 2u, which is 2 cos e to the t squared. Du by dv, I wonder if I've got enough space in this bit of paper to do all this. Du by dv is going to be, so cos v is going to become minus sine v, which is equal to minus sine e to the t squared. So the way I've set this out labels everything for me as I go along. dv by dw is going to be e to the w quite nicely, which is going to be e to the t squared. So obviously e to the w, when we differentiate that with respect to w, it doesn't change. And dw by dt, w with respect to t is going to be 2t. So this tells us that dr by dt, following this recipe here, is going to be 2 cos e to the t squared times minus sine e to the t squared times e to the t squared times 2t. So putting that all together, that's 2 times 2 times minus 1 is minus 4, sine e to the t squared cos e to the t squared. Oh, and then this t would go in here to tidy it up. So yeah, multiply by that final e to the t squared to tidy it up. Woo! So that was a lot of work. Okay, so the chain rule is really good for compounding all this stuff together, taking a big long horrible layered thing like this and breaking it into easy steps and telling us how to combine those easier steps into this final answer. Again, this was a 4-layer one, dr by du, du by dv, dv by dw, dw by dt. You guys will only be asked to do a 3-1 at the most, I believe. Okay, so now we're going to look at some added tricks for tackling special kinds of functions we've not looked at before, using 2 rules called the product and quotient rules. So a product is when we've got one thing multiplied by another, and a quotient is when we have one thing divided by another. So there are proofs for both these things. I'll be honest, the proofs are a bit lengthy and a bit hard to talk through. I think they probably make bad video, bad radio as well. So maybe you guys can research this in your own time. All that's important to know is that the product rule says that if we've got some function h of x is equal to f of x times g of x, which I'm going to shorten down to say that h is equal to f times g. So they can't be functions of each other, they have to be functions of only x. Then h dash is equal to f dash g plus f g dash. In other words, we're going to be using the original functions and the derivative of both original functions in combining this according to this template. So let's have a look at what I mean here. So first of all, what do we mean by h of x is a product of 2 functions? Well, what about something like, let's say y is equal to sine x cos x. Okay, so that's one function multiplied by another function. Something we've not been able to do yet in general. There's been some cases where we've been able to do some little tricks to try and get around it, but this will let us to do all of them all the time. Every trick we've done before should give us the same answer as us doing this way. So what we do is we have a look at this and we say, well, what do I need to know? I need to know what f is, I need to know what g is, and then I need to work out what f dash and g dash are. So here I'm going to say that f is equal to sine x, and g is equal to cos x. So these are the 2 functions that have been multiplied together to give what y is. So then I work out what f dashed is. F dashed is going to become cos x, and g dash is going to become minus sine x. So just differentiating these things one at a time. So then dy by dx then, in other words h dash, is going to be these things put back together again according to this template. So f dash, let's write it out, f dash g plus f g dash. And remember, because this is addition, it doesn't really matter which way round you get these, as long as it's derivative times original plus derivative times original, doesn't really matter. So f dash g is cos x, put these in brackets, cos x times cos x plus fg dash sin x, oops, sorry about that smudge, times minus sin x. So putting that all together, we get cos squared x minus sin squared x. Let's look at another one. Let's do y is equal to x squared e to the 5x. Well, again, we label this up. F is equal to x squared and g is equal to e to 5x, and now we're going to just differentiate this. F dash is equal to 2x, g dash is 5e to the 5x, so dy by dx is equal to f dash g plus f g dash, which is equal to 2x times e to the 5x plus x squared times 5e to the 5x, which is equal to 2x e to the 5x plus 5x squared e to the 5x. And then in the notes I've got a tendency to factorise these things out, so let's make that x e to the 5x 2 plus 5x. But that there is an answer. That's just extra credit for factorisation there. So this is the product rule. Identify which two functions are being multiplied together to get your full function. Write them out. Differentiate each one individually, and then combine them according to this template here. That's every product rule question you can ever be asked. So this is going to come in important. First of all, it opens up all these extra types of functions that we can differentiate now. If we can identify a function, identify that the function is a product of two smaller functions, now we can differentiate using this rule. But it also is going to come useful for certain applications of differentiation. We're going to look at something called implicit differentiation. This is going to pop up once or twice as well, but we'll think about that when we get to it. The quotient rule is similar but different. So if h of x is equal to f of, oops, the quotient rule is similar but different. First of all, it handles a different kind of function. It says what if h of x is actually f of x divided by g of x. In other words, what if h is equal to f over g? And it tells us that h dashed x is equal to f dashed g minus f g dash. So it's looking very similar to the product rule already, but of course life's never simple. Divided by g squared. So as well as turning that plus sign into a minus sign, we are dividing by g squared. So suddenly the order in which we do these things is important, and that it's the f g dash that we subtract and not the f dash g. So keep your formula sheet in front of you when you're trying to do these ones. So let's have a wee look at the application. Let's do a classic one then. Let's do y is equal to tan x. So remember that tan x is actually equal to sin x over cos x. So we're going to identify everything we need first. So f is going to be sin x, g is going to be cos x, f dash is equal to cos x, g dash is equal to minus sin x, and g squared, which is the last bit we need, is going to be cos squared x. So we need this extra piece of information here, but apart from that, it's all just putting it in, just like product rule, putting it into the template we've been given. Again, there's a proof for this thing, but I'm going to leave that to you guys to look up. So dy by dx is going to be f dash g, so f dash g cos x minus sin x for f and minus sin x for f for g dash, sorry, all for cos squared x. That's equal to cos squared x plus sin squared x over cos squared x. And remember that sin squared x plus cos squared x is equal to 1. So that's 1 over cos squared x, if we wanted to neaten that up a little bit. Or, if we wanted to be even stranger, cos squared x over cos squared x would be 1, and sin squared x over cos squared x would be tan squared x. So the trig stuff starts to get a bit kind of exciting at this level. Okay, so that's the quotient rule and that's the product rule. I'm going to put another quiz up, I guess, for this stuff. Maybe get that done by Tuesday, I think. And then if we can get the next lecture up as well, I'll put a quiz up that should be up by the following Friday. So quite a few quizzes to do in a short amount of time, but you know the deal with this, guys. So on Thursday afternoon, I plan to make myself available for tutorial time. The way I see this working is that I'm just going to be about. I don't even plan on doing a group unless you guys want to. You guys will all get on Teams at roughly the same time. We can talk about what we want to do. I can either do stuff one-on-one, or we can, if there's a lot of people asking the same question, I can certainly do a big thing, a group chat. Okay, well this was the next section. We'll talk a bit more soon about what comes next, and yeah, I'll speak to you soon.